The Fundamental Theorem for Line Integrals, Part 1, an Introduction. Let C be a smooth curve given by r of t on the interval a to b. Also let f be a differentiable function whose gradient vector is continuous on the curve. Then the integral over c of the gradient dot dr is f of r of b minus f of r of a. This is a multivariable or a line integral version of the fundamental theorem of calculus, where, if you recall, we said the integral from a to b of f prime of x dx equals f of b minus f of a. That is, the integral of the derivative is the change in the value of the original function. Now, it's pretty easy to see why this is true for single variable if we simply rewrite our notation. Notice that f prime could be written as df dx, and then times this other dx here, which gives us what? Well, this is saying the sum of very small changes in f, right? Which, of course, is the total change in f on the interval given. Well, how do I find the change of the value of a function? Well, it's, of course, f of b, the endpoint, minus f of a, the start point. For a simple example, if I said I started with 2 and I ended with 10, what would be the change? You would automatically subtract to get your answer. So let's do the proof for this multivariable situation. And you're going to see it's going to be similar, or at least the end result will be similar. I'm going to do the proof in 2 dimensions. That is, let f be f of xy. We'll say let f be a differentiable function with all the other conditions that are given in the fundamental theorem of line integrals above. Just not going to rewrite all those. And let r of t equal x of t I plus y of tj. And of course, if I wanted to prove this in 3 dimensions, we would just add z of tk. The idea is the exact same. So we can rewrite our integral, the gradient of f, remember that's a vector, dot dr, so we're going to be doing a dot product in just a bit. But let's rewrite this first as the integral from a to b, so let me add this here on t equals a to b, of the gradient. Okay, so the gradient is going to be the vector f of x of x of t, y of t, and then comma f of y, or the partial with respect to y, of x of t, y of t. And then dot with r prime, or dr, which is going to be x prime, comma y prime, and of course dt at the very end. So we have rewritten our integral. Let's do the dot product on it now. So the integral from a to b of my x times my x, which is going to give me, and I'm going to rewrite some of this in different notation. I could write the partial with respect to x of f as that notation, and I'll rewrite the back notation as dx dt. Same idea, different notation. plus, now continue the dot product, multiply this part times this part. So we're going to have the partial of f with respect to y times dy dt. And then we have this dt at the very end. Now what does this equal? Well, here I'm going to undo the chain rule. That is, what I have in here is the end result of a chain rule. So if we were to undo the chain rule, we would say that this is the derivative with respect to t of what? Well, of f of x comma y. You might want to go back and revisit the chain rule to see that this is indeed the case. And then times this dt at the end. Just like we did with single variable, we can cancel out these dt's. So what do we have? Well, we have the integral from a to b of the change of f of xy. So again, these are very small changes in the function f, and then we add all of these small changes together. So this is the sum of very small changes in f. That is, it's the function at the endpoint minus the function at the starting point. Let's do a couple examples. I'm going to do the more complicated one first and add some extra information. We've done a problem in an earlier video, but not a lot of these. So consider the gradient vector f to equal 2xy plus y squared I plus x squared plus 2xyj. Also, let C be any curve that starts at 1, 1 and ends at 4, 3. And we want to evaluate the integral of the gradient of f dot dr. So in a case like this, we don't actually need to find dr or a parameterization of the curve. We're going to do it this way instead. I want to find the actual function f. So the function f is going to be the integral of the partial of f with respect to x dx. So I'm going to integrate this thing with respect to x, which gives me x squared y plus xy squared plus some function of y only, right? Because if I were to take the derivative of this, the partial of this with respect to x, I would get 2xy plus y squared plus 0. So we have to assume there might be some function back here that's only a function of y. Now, if I were to take the partial of this now with respect to y, we would get x squared plus 2xy plus g prime of y. So we took the partial of this result with respect to y, and we ended up with this. But I know from up here, from my original, that gives me the partial with respect to y, which is x squared plus 2xy, plus, well, nothing else, plus 0. So this implies that g prime of y equals 0, which means that g of y is a constant. So I found g of y. I can plug it back into my f of xy, which gives me f of xy equals x squared y plus xy squared plus some constant c. And now to evaluate my integral, the integral of the gradient of f dot dr over the curve, I can find by simply plugging in the endpoint. So I can do f of 4, 3 minus f of the starting point, 1, 1. So I can plug in, I would get x equals 4, so 4 squared times 3 plus 4 times 3 squared. The constant will subtract off, but we don't need it. And then minus, plug in x equals 1, y equals 1, so we get 1 times 1 plus 1 times 1 again, which is going to give us, if I did this correctly, 82 as an end result. Let's take a look at a much simpler example. Let f of xyz equal xy plus yz plus 2xz, and we want to evaluate the line integral, the gradient of f dot dr, for some curve, for any curve that starts at 1, 1, 0 and ends at 2, 0, 1. So why is this a much easier problem? Well, it's because I know this is simply going to be f at the endpoint, 2, 0, 1, minus f at the starting point, 1, 1, 0, and I already have my function f because it's given in the problem. So if I plug in x equals 2 and y equals 0, we get 2 times 0 plus 0 times 1 plus 2 times 2 times 1 minus, now plug in x equals 1, y equals 1, and z equals 0, giving us 1 times 1 plus 1 times 0 plus 2 times 1 times 0, which equals 4 minus 1, or 3.